be able to do that by voice, but thank you very much. It worked. It did work. It worked very well. Welcome all of you to this public lecture here. This is part of the university's 50th anniversary. We were born in 1964, so I guess 50 now makes us middle age, so that's the way it is. And we've come a long way since then, and those of you who know about the university this year, in the most recent league tables, we went 10th in the country, so top 10. Tonight's lecture is about the bizarre world of low temperature. Now I'm going to demonstrate immediately that I'm not a physicist, because low temperature to me might be -5 or -8 degrees on Colwyn today. I think we're talking a very different scale of low temperature in terms of what you're going to hear. And we have a real honour tonight to have two people who will speak. The first speaker is Professor David Lee, who won the Nobel Prize in 1996 with two colleagues, and this is where I again might display my non-physics background in superfluidity of liquid helium-3, and I think some of that came from work that was also done at Lancaster at the time, so it's very good to have David, who's an honorary professor of ours here at the university, to talk a little bit about what that was like, and then after that Professor George Pickett, who's fellow of the Royal Society, will talk about that work on helium-3. It's going to be very stimulating. Some of you, I think, have had tours around the labs before the lecture now, and there is a tour afterwards as well, so those of you who haven't, I would encourage it. It's really interesting to see, especially as a lot of the kit equipment was built and developed and designed here. But if at this point I could hand over to Professor David Lee. Thank you very much.
Well, it's a pleasure to be here, and I wanted to wish Lancaster University and all the people affiliated happy birthday. We're going to talk about superfluid helium-3 and how it was discovered. Before starting, I'd like to give due credit to my collaborator, Doug Osheroff, as the graduate student. It was a very nice thesis that he had. And we should all have such a thesis, and for his PhD. And Bob Richardson was the late Bob Richardson. Sadly, he passed away a year ago. He was a very active, starting as a postdoc, and then ending up as a professor, and then ending up as vice provost for research at Cornell. And so we had a wonderful group, and we had a great time. Low temperature group at Cornell was a very active time, and everybody was having fun. When I first got to Cornell, there was a sign on the door. I was relegated to a rather, sort of an outhouse kind of thing, a little shack. People were afraid that we worked with liquid hydrogen, which we did at times, and there was a sign on the door that said, there was once a young fellow named Dewar who was very much smarter than you are, since none of you acids could liquefy gases. And then there was no punchline. Think of it. You just have to do something newer. so we tried to do it, and ultimately we were lucky enough to succeed. So there are two kinds of helium, two isotopes, as we say, of helium. They both have the same chemistry. One is helium-3, the other is helium-4. Helium-3 is characterized as having 5 particles, an odd number. That's two protons, a neutron, and 2 electrons. Helium-4 has 6, 2 electrons, 2 protons, and 2 neutrons. You say, well, it has the same chemistry, and the mass is somewhat different. Okay, but why should it behave so differently? And the real answer is, well, you can do it with statistics. Well, statistics don't lie, not electrical physics. The oddness and the evenness correspond to two different kinds. Mother Nature has decreed that there are going to be two kinds of statistics. Bose-Einstein statistics for particles with even numbers of elementary particles, and Fermi-Dirac for odd numbers of elementary particles. I won't go into the more details on that. You can raise questions about that. But anyway, for our purposes, let's think about it that way. Bose-Einstein statistics allows, and as you can see on the next slide, oops,
We go, maybe.
You are using the wrong computer.
Oh, this Merci beaucoup. In the heat of battle, I seem to have fallen. These are the statistics. So bosons, when you're at high temperature, you can see that they stack up at higher and higher energies, and you have more and more occupancy in the lowest energy. And for high temperature, you also, for Fermi statistics, which are a lot helium-3 atoms, let's say, for Bose-Einstein statistics, you have the helium-4 atoms, and you can see that they are that they only stack up like that. So you get to very low temperatures, and you're allowed to have all the helium-4 atoms in the lowest energy state. These are quantum states, and it's like you have little boxes, and each box has a different energy. And when you get to the lowest energy, all or most of the particles are in the lowest energy box. Now, Fermi direct statistics does not allow that, because you can only have one particle in each box. So you get to the lowest temperature, and all you have is this stack. But this stack is well ordered because they're all in a nice, they're all in a nice line there. There are actually two of them in each box. I didn't show you that. But there's another little hitch here, and that if we consider electrons, they have electron spin. Each electron is a tiny magnet. You can think of a spinning sphere, and that acts like a little magnet. But you're allowed, but you couldn't put, and the spin in quantum mechanics has two possible positions, up or down. And you can't have in quantum mechanics, you can't have both of them in the same energy state if they have spin up. But spin down, you're allowed to put two in each state. So we'll come to that fact of little magnets, because helium-3, the nuclei, because you have an odd number of nucleons, will also have a tiny magnetic, we say, they act like tiny magnets. Okay, I'm on the right computer now, so let's move on. Okay, so what happens is you lower the temperature, and let's say I have just at ordinary temperature, I have liquids, and the particles are quite localized, and so we consider, in quantum mechanics, we consider a particle which, the particles have wave-like properties. When I took the quantum mechanics course, the guy in charge said, well, on Monday, Wednesday, and Friday, the electron acts like a wave, and on Tuesday, Thursday, and Saturday, it's like a particle. And some wise kid at the back said, yeah, what does it do on Sunday? Take a day off. Anyway, at high temperatures, these particles are localized. As you lower the temperature, you get what we call, the wavelengths get longer, because there's a relationship called the de Broglie wavelength, and that gets longer and longer as the momentum of the particles gets lower. So the slow velocity means longer wavelengths. So high velocity, short wavelengths, low velocity. So as you get colder and colder, the thermal velocities get lower and lower, and you end up with the wavelengths getting longer and longer. And as you continue, you get these very long waves, lots of overlap. And finally, at the lowest temperature, you get such a degree of overlap that you just have a single wave representing the entire fluid. And this is called Bose-Einstein condensation. And what happens is it's as if you have a bunch of soldiers in lockstep. So the motion corresponds to moving in lockstep. And I just have a picture of that. This was, you can see the little mailing. This was on the cover of Science magazine at the time Bose-Einstein condensation was discovered in cold atoms in the 90s. But anyway, so the blue soldiers marching in lockstep correspond to the condensate, and you have all these guys outside that are not participating in the condensate. And there's a quantity called phase, okay, and waves, if you have these soldiers marching in step, they could all be part of a single wave. And there's a quantity called phase, and if some soldiers are out of step, they don't just go to the guardhouse, but they're told that they're out of phase. And so, and this out of phaseness is is characterized, the phase is characterized by a quantity phi. And there's a function called, this is the wave function. This is a macroscopic wave function. And this was first discovered or hypothesized by Fritz London. There's a microscopic wave function. Don't worry about all this stuff. But the one thing you do have to worry about is the phase. There's a constant phase for the entire fluid, unless it's moving, but we won't discuss that. But there's quantum mechanics on a macroscopic scale. This is the thing to take with you. And all of us low temperature physicists are always looking for new examples of quantum mechanics on a macroscopic scale. Now, one of the things that, I'll just shift over to discussion of helium-3 now. Liquid helium-3, helium-4 liquefies at 4.2 degrees above absolute zero, Celsius degrees above absolute zero. Helium-3 liquefies at about 3.2 degrees Kelvin above absolute zero. And why is that? Well, helium-4 is heavier, so the gas can form a liquid because you have these attractive forces, and because it's heavier, it's not quite moving around so much, and so it can form a liquid. And because of helium-3 being lighter, it's easier for the helium-3 atoms to move around in the gas, but eventually they too form a liquid. If you have atomic hydrogen, if you had stable atomic hydrogen and never recombined, it would stay a gas all the way down to absolute zero. But we are interested in, now, let's talk about the liquid-solid phase transition. People, if you look at the transition from liquid to solid, a very interesting thing happens for helium-3. You notice that curve has a pronounced minimum. That curve is a plot of the pressure versus temperature of liquid helium-3. And above the curve, you have a solid, and below the curve, you have liquid. That minimum in the melting, what you'd like to do, what we would like to do, I think I'm going to back up a little bit and say that how do you cool? What we like to do, it's pretty easy nowadays, and was easy even when these experiments were done in 1972. You could easily get down to 10 or 20 milledegrees, 10 or 20 thousandths of a degree Kelvin. But you'd really like to get colder. So how do you get colder? There was a guy, a Russian theorist named Isaac Pomerantsev, who thought of this idea. He said, okay, what if we compress liquid helium-3 from the liquid phase to the solid phase? And you have to think about this in sort of a peculiar way. This negative slope means as you go up as you pressurize, you get cooling as you pressurize. What is actually happening there? Well, the liquid tends to be more and more ordered because you have quantum overlap. Even in the case of Fermi statistics, you will have quantum overlap. You have quantum overlap, so there are fewer and fewer states available. On the other hand, the solid is only very, very weakly magnetized. You have all these little magnets with the capacity to flip around. So when you go from the liquid to the solid, what happens? This solid looks like a great big sponge for heat. It soaks up the heat. So you compress the liquid and along the melting curve, and you rise up along the melting curve. And what happens is you somehow have this huge sponge that's taking up the heat, allowing the liquid helium-3 to cool. And this is called Pomerantsev cooling. And one of the difficulties in doing experiments with this is you notice that there's that red line. That means you will have a blocked capillary. You can't, if you have capillary, I'm sorry I mispronounced that. The capillary is blocked because if you have your sample and you have a gas handling system outside your experiment, that capillary will give you communication with the liquid. But with a blocked capillary, you will have no communication between the helium-3, liquid helium-3 outside and the helium-3 inside your cell. So you have to think of a trick which allows you to do it. Let me see what the next slide is. Okay. I'm going to, oops, wrong computer. Okay. What I want to do, this slide I'm not going to show. I'm just going to leave it. Don't look at it. Cover your eyes. Basically, So why were we so interested in getting cold? How cold can you get with Pomerantz cooling? People didn't really know. But we were interested in our experiments to study solid helium-3, because all these little magnets, eventually as they cool down, they would organize so that all the little magnets were all lined up. So this was going to be magnetism at very low temperatures. This was our interest. There was, in the wind, people were discussing the possibility of a superfluid transition in helium-3. Let me remind you that there is a superfluid transition, even for Fermi-Dirac statistics. That superfluid transition is called superconductivity. It means that electrons can flow without resistance once you get below whatever, for lead, say, or mercury. Well, let's say mercury, the transition temperature is 4 Kelvin, and for lead, I think it's about 7. Now people, and you're going to see demonstrations of this later on, you can get very high temperature superconductors above liquid nitrogen temperatures. So how on earth would you get, since you're not allowed to, what you can get is you can get pairing. And so when two electrons form a pair, it's called a Cooper pair, because the theory of superconductivity was first proposed, that the relevant theory, that still was a wonderful theory, and was proposed by John Bardeen and Bob Schrieffer and Leon Cooper. And this was and Cooper proposed that you would have pairs. So in a sense, you could say the helium-3 atoms or the electrons or whatever they are, they can form pairs. And that would act, and then they would basically act like bosons. Technically, they're not bosons. They're not Bose-Einstein. They don't obey perfect Bose-Einstein statistics, but it's close enough to make a difference. So you do have superconductivity, and that's exhibit A. So the question was, would you see this in liquid helium-3? Would you see a superfluid transition? So the competition, of course, was John Wheatley, and he was our arch rival. And this was, now the drama thickens. So John Wheatley tried to do an experiment, did a lot of experiments at low temperatures, very low temperatures, using what we call paramagnetic cooling. And he was able to get down to a temperature where one would expect to see superfluid helium-3, but he never saw it. One reason being he never raised the pressure and worked at higher pressures. Now that was our arch rival, of course, but we didn't expect that anyway, because everybody, by that time, the theorists had argued that the transition temperature would be so low that you never get there anyway, so it was hopeless. So we were sort of running to look at solid helium-3. We went to a conference in Moscow in 2010, the 10th International Conference of Temperature Physics. It was way back, I don't know, 1966, I believe, 1966. And we were taking the train back from Moscow to Helsinki, and Wheatley was on the train, of course, our arch rival. He put his hand on my shoulder, and he said, where else am I going to do Pomerantz cooling? And my heart sank. I had a more immediate problem, however, because my professor said, oh, I have all these rubles and I'm leaving. Could you change them to dollars? I said, oh, sure, why not? Okay. Then I had all these rubles and we were riding the train. Then I discovered you were not allowed to take rubles out of Russia. So what am I going to do with these guys on rubles? And I thought, and I said, well, I can put them in the magazine rack. They had a magazine rack with a lot of communist propaganda. And I said, well, I can put them in the magazine rack. And then I said, well, okay, I'll just think about this a little bit more. Well, the train came into a station called Viborg. Previously it was Viborg. It was part of Finland, part of Karelia. But in fact, it was then, in World War II, it became part of Russia. So I got off the train and I said, what am I going to do? I was sort of walking disconsolately around the platform, and I saw this little lady way down at the end of the platform selling something. So I went down there. She was selling vodka. I said, I will convert my frozen assets to liquid assets. So I give me all the vodka. I give you a handful of rubles. You give me all the vodka I can carry. And she did. So I carried all the vodka. And we got on the train again. And the train came over to the border, the Soviet border with Finland. Of course, they had these machine gun towers every 200 meters, and the plowed strip, the usual thing, and the soldiers came on board. The first thing they did was head for those magazine racks and go through them every single page. So we got through, but then what they should have done was taken the vodka, because they could have had a heck of a party. The minor colonies in Finland, everybody was sort of slapping each other in the back in the free world. This was the height of the Cold War. And we finally got into Helsinki, and the boys were young. Jim was 3 and Eric was 5. And so they stayed in Finland by good luck. That was a good thing for them to have done. They came to meet me at the train. And I said, well, everybody has a job. Everybody has to carry the vodka. So we all carried this vodka back, and we gave it to our Finnish friends who had been looking after Donna and the kids. And they had a heck of a party, so we heard. Anyway, getting back to physics. Because this story has an interesting ending. How do you do this? How do you do this Pomerantz cooling? You have to avoid having a blocked capillary, sorry, mispronunciation. So you had a capillary line here, and this is the cell, but it was blocked. That was actually advantageous. So it essentially isolated the region. It isolated the region where the sample was, and then you compressed by applying force. This was basically a hydraulic press, because you can use helium-4, which if you had a large enough, I won't go through the technical details, but you use helium-4 to drive that piston, and it went down and pulled, and the bellows expanded, and you had, as you lowered the temperature, as you increased the pressure, you started forming solid, and by good fortune, this was an enormous degree of good fortune, because the solid formed in isolated regions, and so we were able to actually study the liquid and the solid. And Doug Osheroff one night was pressurizing his cell, and there was a little, if you notice at the very bottom, you can see it says pressure gauge there at the very bottom. So there was a pressure gauge. And so if you look at that plot up there, you will see that the pressure versus time changed. And as it changed, there was a little glitch in the pressure. And that was called A, point A. And then the next glitch was a rather odd-looking, very fast-looking thing. And that we pretty well realized at the time that had to be supercooling. But since it was a solid, we thought it would be the solid that was doing all these things. Why would the solid supercool that fast? Then on the way back, you just had a flat region, and then you reproduced, and then you had the mirror image of the change in slope on the other side. So that little flat region corresponded to what we call a first order phase transition, and that corresponded to the fact that hesitation, this was a hesitation, that flat region was a hesitation, and what that meant was that there was a latent heat there. So it stayed put for a while. It's like when you melt ice or something like that, it stays at the freezing temperature until all the ice is melted. Okay, let's move on. Let me go back. So anyway, was this the liquid or the solid? Well, we published in Phys Rev Letters. We were worried that Wheatley was breathing down our neck, which he in fact was. So we said it was in the solid, which was in Phys Rev Letters, of course. Very embarrassing, because we were diametrically wrong, as it turned out. But on the other hand, we were not unaware that it might have been in the liquid, all these wonderful little effects on the melting curve. So let us just relabel things. The region between the first, as you go from left to right, from the change in slope to the little supercooling thing, that we will call the A phase, or whatever was happening. The next one, B, is that the B it corresponds to the B phase, or whatever was happening. And then we go back into the A phase when we have that little horizontal region, and then back into the normal, what the normal fairly liquid, or normal, whatever it was, the non-super, whatever it was. So we didn't know. We said it was solid. We were diametrically wrong, I said, but we obviously were worried about it. And we said, we've got to get somewhere. We've got to do an experiment which enables us to determine what was really going on. So we did. And this is the actual cell which was used. And you can see the flexible bellows up top, and you could push that down and thereby compress. And we had coils there, and studying magnetic resonance. and we had a field gradient. Now let me say a little bit, we were doing magnetic resonance. How many had MRI? When MRI, you call it magnetic resonance imaging. Only 2 people here? What a healthy bunch of people. It makes a lot of noise and so on. And magnetic resonance imaging required, we believe, I mean, we did, this is probably the first physics experiment which used an MRI. And actually, when we were doing the experiment, we were visited by Paul Lauterbur, who was one of the people who received the Nobel Prize for this. And of course, the other recipient was Sir Peter Mansfield. You've heard of him, I'm sure. And so but anyway, when Paul Lauterbur was thinking about this, I think he was pretty excited when he visited our lab. And we were excited that he was excited. But we decided that we'd stick with helium-3 and not be biologists. So we weren't rich because of that. But anyway, the idea, the important thing is that you have a gradient in field. The top of the cell, the magnetic field applied was smaller than at the bottom of the cell. And in magnetic resonance, the frequency, you tune in various regions of the cell because the frequency is proportional to the field. So if the field is small, you have a lower frequency. If the field is large, you have a higher frequency. So by studying the frequency of a magnetic resonance signal, you can actually determine the location of whatever is going on. And this is the thing that we did. And to study, because we really were worried about it. I mean, everybody said, well, it could be the liquid, and another guy said, yeah, it could be the solid. And we said, yeah, well, it could be either one of them. It doesn't matter. We better find out what it really is. And so the unfortunate thing that when this experiment was being put together, a leak developed in the exchange gas came. And we couldn't find the leak. We couldn't stop it. One of the youngest guys in the group said, hey, I want to get into the game. Why don't you let me try to fix that? It was Willie Gully. And he said, why don't you let me try to fix the leak? He got the usual glycerin and soap. The way we low temperature physicists, when all else fails, you get a mixture of glycerin and soap. And you just slop it all over the whole can. That was done. The leak stopped, and the experiment worked. Remark about magnetic resonance imaging. In 2003, I think Tony Leggett got the Nobel Prize. He was a great theorist with a wonderful theory of this. He invited us to go to Stockholm with him, and when we were there, Lauterbur and Sir Peter Mansfield got the Nobel Prize in medicine for magnetic resonance imaging. So we decided to go over and listen to the lecture because we wanted to find out more about what they were doing, in case we ever needed an MRI, which we did once or twice. It was very exciting, except that when we were trying to get on the bus, going to the lecture, Nobel lectures, the guys on the bus, get off the bus, get off the bus, we don't want you. And I said, what's wrong, what's wrong? They said, who are you? And we told them who we were. Oh, I said, we thought you were friends with Domadian, you were going to try to disrupt the proceedings. Domadian was a guy who got a lot of patents for MRI, but he was not among the people who decided that using a field gradient was necessary. So he didn't get the Nobel Prize, and they thought we were going to raise holy heck, but we didn't. So that was another exciting incident about that. But moving on, we did the experiment, and I will show you. One of the things is we said that one of the things about Pomerantz cooling, which I should mention, is why do you get cooling? Because as you solidify in this region where the melting curve slope is negative, when you solidify, you're forming more and more solid. The solid has all those little elementary magnets, and they're they serve as a sponge, and so they can suck the heat out of the liquid helium-3, and you end up getting cooling. That's how Pomerantz cooling works in a nutshell. It's a somewhat, one can do it properly. Anyway, this is sort of the way it works, and so you can imagine how you might get cooling doing this. Anyway, what happens finally is that as we cool down, the solid has a very, very large The solid was localized at one end of the cell, so you can see that enormous peak. Solid helium-3 has a very, very large magnetic signal. So that peak corresponded to where the solid was located. If we didn't have any solid in the cell, that dashed line is the all liquid signal. But as you cool down, as you cool down more and more, and this is and you look, delta P is the pressure in the Pomeranian cell. But that corresponds to cooling. As you pressurize, that means cooling. You cool more and more. Each of these signatures corresponds to a different temperature. When you finally got to a certain temperature, the magnetic signal of the liquid, you can see the dashed line, shrank by a factor of 2. And that was a signature that something, what sure as heck was going on in the liquid. Yes, it was in the liquid. And so this was now turned out to be the superfluid phases of liquid helium-3. And I have to say that not only did this happen in Helsinki and in Viborg, but it also happened in Ithaca, New York, because we're now allowed to change our solid assets into liquid assets. Somebody got that one. You're supposed to laugh. Okay, that's what happened. And so Doug Osheroff was going over the data and told me at about 3 in the morning, he told me what he had seen. I said, my God, I'll come right to the lab. He said, don't bother. I mean, I'm just looking at the data. I said, okay, look, this is the real McCoy. And so that was good. So the next thing we did was to go down. So this is the region of the B phase. So the B phase had this situation develop, and we were pretty sure of the B phase. We were now absolutely sure that the B phase was liquid. And now let's move to the next one. So what about the A phase? Well, we got rid of the gradient. We took the gradient away. Okay. And what happened? Okay. If you look at that if you look way over on the left, you see that dash signal. That's the all liquid signal. And the big, huge thing there is a spike associated with the solid. Now, as you lower the temperature by pressurizing, you can see that a little signal, all liquid signal, seemed to be moving out farther and farther away from the solid peak. Wow, that was exciting. And this really was really so we plotted, and the frequency was plotted, and I wanted to show you what that looked like. And we could do this experiment in a number of different magnetic fields, so not just one magnetic field. This experiment was maybe 4 or 5 magnetic fields, I don't remember. And it turns out these are different frequencies corresponding to different NMR magnetic fields up there in the upper left-hand corner. And you can see all of those points fell on a universal curve. This was exciting. And so the whole thing was wrapped up. And I will show you some other point. A lot of people had trouble with it. I had trouble with it myself. But let's just at least try to talk it through. We have the applied magnetic field, and then the magnetic field, the effective magnetic field of the liquid is that diagonal line. And when you look at this, you can see that there's a horizontal line, which is H int and H int. You look, you plot these things, and HINT and HINT is always the same. That's telling us that there was an internal magnetic field. That's what we thought. And then if this would mean that if you turn the applied magnetic field down to 0, you should see a longitudinal magnetic resonance. In other words, you have your coil, you have a magnetic resonance coil turned in one direction. Let's turn it in 90 degrees, and then you should still see the signal. This was observed later. This is what we thought at the time, but I'll move to the next slide. I think that, so these are the nuclear, the Cooper pairs that are formed have different configurations. I think I will not go into that now, but except to say one thing, that there are 3 different superfluid helium-3 phases, depending on the function of the magnetic field and the function of temperature. So we now had Cooper pairs of helium-3. The difference is that they were going around each other like that, rather than the electrons in the superconductor that were going by like this. The helium 3 atoms had angular momentum around one another in addition to their electron spin. Many of these effects were studied, for many, many years, and it was a very exciting time, which here in Lancaster, a lot of these experiments are still going on, and very exciting research is happening here in Lancaster. So again, happy birthday for your 50th anniversary. We wish you all the best. Thank you.
We're not trying to avoid our responsibilities, but I think it's better if we don't take questions. It's quite intimidating to ask questions like this, but come and speak to us afterwards in the nibbles and, you know, on the tours. Okay? That gets rid of the awkward questions. Jacket, so you don't need to see it anymore now you know I've got one. Dave paid you a tremendous compliment there by assuming that you're as clever as Texans, but I know about Lancaster, so we probably do quite a lot of the same things, but slower rate, okay? Now, liquid surfaces come into this, but most of this is really just to demonstrate our qualifications that the graphics in this thing have not been stolen from the internet. They're home produced. Okay. So, we won't jump straight into superfluid helium-3. We'll start at room temperature and do some nice, easy things. And to do that, I'm going to use my companion here, Victor Zeppelin. He's an epitome of the European situation at the moment. He's half Estonian, half Russian. So Mr. Putin may rush in and rescue him in the middle of the talk. Okay, so let's do the old favorite, flowers in liquid nitrogen with. This is liquid nitrogen in here in a pure flask, and it comes in things like this. And you tip them over and the liquid helium comes out. And while we're on the Russian stories, I went to a conference in Kazan once, and we had a picnic on the day off, and we all went in a boat to an island in the Volga, and they took 2 of these with them. And I said, why the hell do you need liquid helium or liquid nitrogen for the picnic? That's the vodka. Okay, let's choose flour. If any of you are health and safety experts, you haven't seen this. Glass also. Okay, so we're just going to looking exactly the same as it went in, but it's now a glass. And if you go on the tour, you can do this yourself, but you probably have to wear the goggles, otherwise we get sued by your insurance company. But It's not altogether trivial. I mean, biological systems are rather nasty, and somebody's not going to thank me for putting this all over the floor here, because it's, you know, cells are nasty things. They're half water, they're wet, they're wobbly, and you leave them in the lab overnight and they go moldy. And doing this sort of thing is one nice way of studying cells. You cool the cell down until it's frozen, then you cleave it, and here's a nice picture of a cleaved cell. You can see all the structure of the cell. You know, we couldn't do trying to do it with a razor blade and glue. Okay, so let's see what happens with metals. We'll start with a stainless steel ruler. Okay, here's a stainless steel ruler. I can bend it and it comes back again. And I'm just distorting the bond, so I'm doing something like that. And if I do it with a lead ruler, here's a lead ruler, I'm trying to bend it and, oh shit. Going to go back again. And the ruler won't return to its original shape. It does that, and then, oh, the bonds are broken. And that's because it's close to its melting point and the bonds are weak. Okay? We're starting very gently, right? But this is Lancaster, I know. Okay, I should have a handbell to do this, but I don't have one. But a handbell must resonate, which means not breaking the bonds. It's got to stretch, and then it's got to come back again, okay? So I've just demonstrated that a lead bell isn't much good. Its bonds aren't strong enough. And by some mystery, here's one that I made earlier, or our chief workshop. That's a lead bell, right? Not blue, bell. You ready for this beautiful noise? That's rubbish. Okay? You trust me to do this, or are you going to do it? Faster, faster. Try. So you could have had another cold one ready, but you wouldn't have believed it then. And your feet getting cold at the too bad. Okay, now for some more serious stuff. And this is to introduce you gently to what's coming later, because the difficulty of this talk is graduated, right? And you'll have to forgive me, I'm used to, physics is a very international subject. So usually I'm speaking to people who are not native English speakers, so everything I say is repeated on the screen. So it's not that I'm thinking you're idiots. Well, it may be, but that's not one. Okay, so this is dropping a magnet down a metal tube. And where did I put all the metal tubes? Give me the stainless one first. Where do you put the magnet? We needed something like that. Okay, this is a stainless steel tube. This is a very high power neodymium magnet, and I'm going to drop it down the tube, and it comes out of the bottom. Nothing special, right? That's okay, we're doing it. Now this is a copper tube. This has much higher conductivity. And I'm going to wave a magnet near a piece of metal, right? And that's, crudely, that's an electrical generator. If I wave a piece of metal near a magnet, that's a motor. And if I wave a magnet near a piece of metal, that's a generator. Let's get back to that. So we'll count it. I drop it now. 0 and 1 and 2 and... It was a bit slower, right? And you can be doing that while I'm doing this. If I drop it down this big tube, 0 and 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8 and 9 and now. Okay, so we drop the magnet down a copper tube, and when we drop the magnet tube, we get these eddy currents, what I put here with the arrows, and this generates another little sort of effective magnet in the current on the wall. So I get, there's my north-south in the middle there, and then the eddy current above gives me a north-south there, which pulls it up, and the eddy current below gives me a reverse one, which pushes it up. So those eddy currents stop the magnet falling so fast. Now, copper is a good conductor, so these currents last a long time. Stainless steel is a crap conductor, so almost nothing happens when we put it down. But my friend Victor here, okay, we cooled the tube down. This makes the electrons run much more freely fluid. And it was 2 seconds before, wasn't it? Okay. 0 and 1 and 2 and 3 and 4 and 5 and 6 and 7. Not bad, eh? Okay. Okay, these currents die out rapidly, but they last long enough that they create a magnetic field that holds the magnet up. And yeah, if you make the currents last longer by cooling the copper, you will notice I've said this already, but it's there in case you didn't get it first time. I teach students here. And you could be thinking what would happen if the currents in the tube simply didn't die out, but kept on flowing forever. Okay? Okay, this is just a taster to get you started gently. And now for the real story. So we have to keep up to the latest tricks with students here because they're so savvy at the latest media. So this is what is called DA credits, as you know. So here's our team that you're going to meet. It's probably illegal to use that logo, but never mind. Parental guidance, I reckon, was that. Okay, so we'll up a sort of here. So this is the context. So here I've got a logarithmic scale. So this is scale goes up in factors of 10, which is the only way I can put the whole temperature scale on one thing. This is inside hot stars, which is billions of degrees, and right down to 10 to minus 10 degrees. And this is measured in Kelvin, which is degrees Celsius stroke centigrade for dinosaurs above absolute zero. And this is 1 millionth of a Kelvin above absolute zero, 1 microkelvin, so that's 1 millionth. Sorry, that's 1,000th, a millionth, and a 10 to the 9th, whatever that is. And the universe, according to today's theory, starts with the Big Bang, essentially at infinite temperature. And since then, it's rolled down, it's got to 2.7 Kelvin today. So that's about 3 degrees above absolute zero. And standing in this room, we're about 300 degrees above absolute zero, because we're not in outer space, we're near the sun, which happens to be anomalously warm. When you look at the sun, you see white light. Now, if you're a child at school, you paint the sun yellow, because the blue light coming from the sun gets scattered. So that spreads out all over the sky. So the sky is blue, the sun's yellow, but you put them all together, that's white. And that's equivalent to about 6,000 degrees, which is the temperature of the surface of the sun. If you work in a blacksmith shop with iron, you can make it a few hundred degrees, that's red hot. But if you look out on a dark night, between the stars, it looks black. And that's only 3 degrees. That's the sort of radiation that's coming, that's left over from the Big Bang. So it's a lot colder. Okay? And our little bit, life, the universe, rice pudding, income tax, it just sits in that little green bit there around 300 degrees. So this is the context. But the point I would like to make is, look at these two regions. That bit's happened already. High energy physicists are looking at the top of that and quite a long way up off the top of the scale, another 10 orders of magnitude with the Large Hadron Collider. And this bit down there, Mother Nature has never sampled that bit. The universe has only got to the division between the two. So we're talking about sort of futurology here. I once told our press office that an alien landing in Lancaster could tell that there was intelligence here, because if they knew that we were working at millikelvin temperatures in the physics department, this isn't a sort of normal natural process. You know, universe has only got to 3 degrees, so it would demonstrate that we had intelligence. I mean, you should never talk to the press office. An article came out, intelligence discovered in physics. Okay, so now let's look at some real low temperature. And we'll introduce a bit of Mickey Mouse quantum mechanics. Okay, we're doing this gradually, it's racking up. So let's say we think of an easy liquid, water in a bucket. In the water in the bucket, without going too much, and if you want to know, you can sign on for physics here, but there are lots and lots of energy levels determined by the quantum mechanics, and the water molecules just have to distribute themselves some way among these energy levels. Okay? So this is the Mickey Mouse picture in quantum mechanics of water in a bucket. Let's rotate the bucket. That's the Lancaster. What happens? There's a gradual redistribution of molecules. The one hitting the bucket gets kicked the way the bucket's going. And you know this takes a long time, but after a while, this spins up the water until it's rotating with the bucket. So we can see that the quantum mechanical states which are occupied are being churned up because we're trying to get them to go around in a circle. Okay, what happens if we cool the liquid down towards absolute zero, which is the whole point of this talk, isn't it? The molecules, as they cool, will move into lower and lower energy states because the temperature is going down. And of course, if it's water, that's a flop because it freezes and that's the end of the story. But if it's, say, liquid helium, which stays liquid right down to absolute zero, what will happen? Well, something odd must happen at the very lowest energy states, because as we get down to lower and lower temperatures, all the particles are trying to go into the lowest energy state, which, think of the bottom two there. We can think of temperature as the shaking effect of the outside world. So these poor little molecules or atoms, if it's helium, are trying to distribute themselves in various states. And if we leave them very quietly, they will all go to the bottom. But if there's a higher temperature, we're shaking the little buggers like that, and they go all up and down. So as we shake less and less, they shake down to the bottom. And when the shaking effect or the temperature gets less than the energy gap between the last two layers, then they all go into the bottom state. You with it? You're going to be tested on this afterwards. Papers ready. Okay, that's what I said. So all the atoms are in the same state at this point. And this is what Dave was saying with these guys marching into step. But there's no dissipation. They're all moving together, so they can't collide with each other and slow each other down. They're all doing exactly the same thing, right? Okay, there's no friction. So this liquid is a superfluid. It has zero viscosity. Once this liquid starts to flow, it can flow forever. And I'm not joking, that is serious. Scary, isn't it? Okay, and immediately you would say there's no friction. We can see this immediately, and I should have a video of this, but they're all crap. So what I'm drawing here, there's a beaker here, which I can lower into superfluid helium and pick up again and fill it with superfluid, right? And I have a convenient glass here. I put some water in. I shouldn't make the vodka joke, should I? This is water. If this glass is in normal atmosphere and it's full of water, there will be a thin, a few molecules thick layer of absorbed water all the way over the whole surface of the glass. And it doesn't matter to normal men. But if we make that without friction, this just acts as a siphon. So here's our glass here. Here's our superfluid, and the superfluid just runs up and down and off the bottom. And that's what the drips off the bottom are. Those of you who are attending will notice. So you can't contain this stuff in an open flask. And those of us who work in this field know that if there's no friction, this damn stuff can go through any hole in your apparatus, which is of molecular dimensions. So we have the most dreadful job trying to get rid of leaks. And one of our big cryostats, we have one on at the moment, we've been chasing for months, and we don't even see the helium coming through until we've been there cold for about 10 days. And it's very difficult to find. This is, a few atoms wide hole in some piece of metal. So this is sort of obvious thing, the low friction. But a more fundamental thing, and this is what Dave was telling you, but he assumed you understood immediately, that they're all in the same quantum mechanical state, and the whole liquid is behaving as if it's a sort of big molecule all moving together. And this wave function thingy which describes the behavior can be pictured as a sort of map of some imaginary angle called the phase. Now, so here's our imaginary map, and this is the phase angle. So, this is a picture of Ingleborough, if you like. If the liquid was just calm and not moving anywhere, this would be completely flat. So this is a pretty unhappy bit of superfluid, but it makes the point. And it's not quite as weird as it sounds. We're quite used to using angles to think of quantities in everyday life. I mean, the obvious one is time. We think of time as an angle. You know, 12 o'clock is up and 6 o'clock is down, and other things are somewhere in between. It's no more than that. But the flow of this superfluid is governed by the gradient of the angle. Well, that's why I drew this as a contour, because the gradient is just downhill. And this has an immediate important consequence. If you stop to think about it, you can't run down a hill and go round in a circle simultaneously. Because if you go round in a circle, you end off back where you were, and that's up, right? The only way you can do that is you need a spiral surface. If you go down a spiral surface, you're going down and you're going around in a circle, but that's not a normal surface like you would see on the sides of Ingleborough. And that means, in simple terms, that a superfluid cannot be rotated. Now that's a rather strange concept. That's supposed to tell me something, but I don't know what it's telling me. Never mind, not to worry about it. Oh yes, it tells me that. This raises the philosophical question of what rotation is, okay? We all know it. But, I mean, relativity tells us that we can't tell if we're moving in a straight line with a certain velocity. We're moving around the sun with some colossal velocity, but we don't have to worry about it when we drop our keys on the floor, right? It behaves as if we're stationary. We can't tell, but we can certainly tell if we're rotating, because we can take two balls rotating in the universe, tie a piece of string together, and we can check out what the tension is in the string, and we can just, through a simple equation, tell how fast the rotation is. And you see what happens to that force if we abolish the universe around the spheres. You see, once we've abolished the universe, the spheres can't be rotating because they're the only things there is. So this force must gradually disappear. We don't quite understand that. But that means if we have a complete empty piece of space, the two balls know what stationary and what rotating is, which is, how does that happen? Well, we'll come to that later. Anyway, this liquid is non-rotating in the frame of the fixed stars. So it's the perfect inertial navigation medium. And in fact, with the laser-cooled gases, which are very similar to this, people are working on making those for submarine guidance at the moment. It's not totally stupid. But what I said isn't quite true. This contour diagram we had was actually an angle as we went up and down. And now as we go through 360 degrees, we get back to where we started from. So if we, that's not mine, is it? No. It's a subtle message from the chairman, I think. Okay, if our circular staircase goes down 360 degrees in this contour map, we do get back to where we started from. So that's okay. But this is going around in a circle. This is a vortex. So we can have vortices in the superfluid, but not rotation. And this is interesting if you haven't thought about it before. But you see, the problem with the spiral staircase is that the gradient gets higher and higher as you get towards the middle. And in the middle, it's infinite. And these poor medieval masons cop out at that point and put a pillar down the middle, right? That saves them some tricky geometry there. All vortices have to have a hole down the middle. Otherwise, the velocity near the center exceeds the velocity of light. So when the water runs down your bath, thank your lucky stars it doesn't fill the whole hole, because it would probably vaporize you in the house and everything. Okay, in a vortex, the rotation of the liquid is confined to the axis, and this is a quite an interesting point. In solid body rotation, okay, we've got our bucket going, and the whole bucket is moving, all the liquid is moving around with it, and we can apply a vector calculus operator to it called a curl, which would tell us what the rotation is, or we can make a simulation of it, which is we just shove a cork in the water with a cross written on top of it. That's a complicated mathematical operation. But and as you notice, the cork rotates the same as the bucket rotates, right? And that will happen wherever the cork is in the bucket. So the rotation in the water is uniformly distributed over the whole bucket. Yeah? Yeah. Right, now let's say I just bash a hole in the bottom of the bucket and I let it whizzle out with a vortex. Now if I watch my cork going around, it doesn't rotate, because the water goes around faster towards the middle, and that just counteracts. And you imagine that if a boat's going down the maelstrom, it goes down like that. So there's no rotation in the liquid. The cork is going round and round, but it's not rotating. And until you get to the axis, so it spirals down there, and whoa, now it's rotating. So in the vortex, the rotation is zero everywhere, but all down the middle. So I can fill my, oh, I'm not supposed to have said that yet, forget it, I haven't been trying to yet. If I want to rotate my superfluid, I can sort of simulate rotation by putting lots of vortices in. But the rotation is just down the core of the vortices, and the rest of the liquid is still not rotating, which is an interesting point. Right, now I've been lying to you, that's I can say that. It's a bit more complicated than I've been telling you, and Dave's alluded to this already, but it's more interesting. Now you see, Dave said it was Mother Nature. We're more conservatives. I said it was God. But God's told us there are two different sorts of particles, and we can call them what you like, 1 and 2, anything, red or blue, doesn't matter. The pompous names are fermions and bosons, and we've all heard about the Higgs boson. But, so you don't know this stuff anyway. The building blocks of matter are fermions, so this is protons, neutrons, electrons, what makes up chemicals, rice pudding, going back to what we're doing. And the other particles are bosons. This is photons, gravitons, gluons, all these stupid names. These are the ones that carry information. And I can illustrate this. This is a high frequency area, okay? And I'm pushing bunches of electrons up and down it, yeah? That's running the arrow by putting a current in it, yes? Please look as if you understand. Okay, that generates a radio wave going out there, which you can just about make out. And those are photons. Okay, they're very long, low energy radio frequency photons. And in my receiver somewhere else, I'm going to pick up these photons, and that's going to make the next lot of electrons go up and down and give me the signal, right? And this is just a demonstration. The fermions are the electrons. What they are doing is being transmitted by the photons, so they're the telegraph system, the messengers, and then they tell other fermions what's going on, okay? So these photons and such like are telling the rest of the world what these particles are doing. And these two particles behave in different ways, as Dave pointed out. There can be any number of bosons in one quantum mechanical state, but there can only be one fermion in one state. And we can demonstrate this. So these are some energy levels. And if we try and put, this is energy levels in our bucket, for example. If we fill the bucket up with fermions, we can only have one per state. If we fill it up with bosons, we can have more than one per state. So, if we try and put more of the electrons, we get the periodic table. If I have an atom with a single electron in it, it's hydrogen. if I put 2 electrons in, the next electron has to do something different, has to be in a different state, so that's helium. The next electron has to do something, that's lithium. If they could all go in the same state, all atoms would look the same, but some would be big and some would, you know, they'd be grey sludge rather than elements. But, you see, if we're trying to take our laser on our Humvee, we can take out, you know, Taliban roadside bombs. You know, a laser full of photons, which are bosons, if I can only have one in this laser, that's not very impressive. So you know, from your own experience, you can see that these things happen. But for many particles together, say in a liquid, this only matters at low temperature. If I have only one particle per state, it doesn't matter when they're allowed to have 1 or 2, you know, there's no competition. But if I go to low temperatures, the fermions can't have all the states in the ground state, but the bosons can. And we said if they all go in the bound state, they could be superfluids. So these can form superfluids, and these can't. And as Dave told us, bosons and fermions are distinguished by their intrinsic spin. We can think of them as they're spinning. There's a quantum number for spin, and bosons have an integral number, and fermions have a half integral number. So 0, 1, 2, 3, 4, 5, 6, that's integral, and half, 1.5, 2.5, 3.5, 4.5, that's half integral. And this is where helium comes into it. The helium-4 atom has 6 particles, they're all fermions, they all have spin 1/2, so however we add them up, that's going to be a whole number. So the helium-4 atom is a boson. And if we take the light isotope helium-3, that has a neutron missing from the nucleus, so that's an odd number of spin 1/2 particles, and however we put them together, that's a spin 1/2 particle, and that's going to be a fermion. Helium-4 occurs in nature, and helium-3 is extremely rare, and it's a byproduct of, it's a decay product of tritium. The point which Dave made is that just this quantum mechanics means that the behavior of these two things, they're chemically identical, but at low temperatures their physical behavior is completely different. And that means at low temperature, liquid helium-4 can form a superfluid, no problem, at around 2 Kelvin, that's 2 degrees Celsius above absolute zero. But helium-3 can't because it's made of fermions. Well, at low enough temperatures, these crafty helium-3 atoms, they can join together in pairs. These are these famous Cooper pairs. If we take 2 half-integral particles and plug them together, they make a whole particle. So these pairs are now bosons, and they can form a superfluid. But this all happens at much lower, 1,000 times lower temperatures. Okay, so the superfluid helium-3 is made up of these little pairs, all in the same quantum mechanical state. And you can think of them as, you know, they're dancers in a square dance, so you can see your partner over the other side of the room. You know what she's doing or he's doing, you know, but there are lots of others going on in between. So they're loosely connected, but they know what their partner is. Are you ready, young Victor? This brings us back to the beginning, because electrons in metals, which are fermions, can also form these pairs. And that means they can flow without resistance. And that means the metal becomes a superconductor. Has no resistance, therefore electrical currents flow forever once started. Now, that means that the eddy currents in our copper tube would not have died out, they would have just stayed there, in which case our magnet would just have been levitated halfway down the tube. Now, I negotiated with a company in Prague to buy a bit of high TC superconducting tube to generate this, but it was 600 euros, and you know, I didn't think you were worth it. So the committee wouldn't have paid for it. But we can do it the other way around. We can make a railway track. So this is we have the magnets there in a railway track, and we'll float a superconductor on top of them, like so, and it will levitate, and we'll just give it a push, and it will go around. Isn't that fantastic? But you see, we have one here that I prepared earlier. Right, Victor, over to you. There's a 50-50 chance of this working. You shall Putin and put it down. This is just a concept. You have to imagine this as a railway line going from Lancaster to Berlin, but you know, we're working on that. And of course we can unwind a coil of this stuff, run some current through it, and by a sneaky trick we can join the ends together. And there's no dissipation, so this current goes on forever. So that's what the magnet is in your NRR coils when you, or if you're in Texas, you get pushed in one, see what's gone wrong with your whatever it is. So I mean, these superconductors are really the most widely used probably of all the low temperature technology we have at the moment. I mean, all very high field magnets are made with this stuff. Okay, and just as a final, we'll look at a real microkelvin experiment because I've been telling you about the sort of ideas. And we do many experiments here in Lancaster with a vast range of sort of different ideas to do with the superfluid. But this particular one is cosmology in the laboratory. And let's start by looking at the fundamental forces of nature. So we have the strong force and the weak force, which we don't come across in everyday life, which are going on in sort of nuclear level. We have the electromagnetic force, this is the force between charges, which is the sort of strongest force going on in chemistry, so that's what holds us together. And if we measure them as a function of energy, which we can do with sort of high energy physics techniques, we find that they all appear to converge at high energies. And that suggests that in a high enough energy universe, these forces may no longer be different, they may all be the same. And quite where gravity fits in this, no one has any idea, but at sort of low energy, gravity's off the scale here. Now, gravity is what keeps us stuck on the floor, so we tend to think of gravity as a big force. But here's a little lad. He's about to put his hands on one electrode of a high voltage generating machine. And he puts his hands down and his hair goes up, right? We've all seen this. You take a piece of plastic and you rub it on your cheek jeans and put it over your head and your hair all stands up. Now that's a few miserable electrons that you've rubbed off onto another bit. It's holding up your hair against the whole gravitational force of the planet. You know, gravity is pretty weak. But we know that the early universe started at high energy, so it looks as if all the fundamental forces were the same then. And this suggests that after the Big Bang, the universe went through some sort of transitions as these forces sort of peeled off and became distinguishable. And that's just what happens with helium-3 when we cool the liquid helium-3 down and it goes through this superfluid transition. So it's not exactly the same, but it's very, very similar. The sort of mathematical structure of the wave function of superfluid helium-3 looks very simple, similar to the mathematical structure of the metric of the universe, for a better word of putting it. So we can use the superfluid helium-3 as a tabletop model of the universe. And that's useful because we can't rerun the Big Bang, right? It's done and gone. So, and this is simulated brain annihilation. Okay, don't get too stressed. You need 2 more bits of information to understand the next bit. This superfluid helium-3 is complex because it has a little diameter, so it has all sorts of things that can be a bit different. And it has 2 common phases, the A phase and the B phase, which Dave was telling you about. And by some cosmic fluke, the A phase was thought up by Anderson and Morel, and the B phase was thought up by Bali and Wertheimer. So it's not the D phase and the Z phase, which makes life a lot easier for simple guys like us. Now, both these phases are sort of perfect fluids. You know, the atoms are completely delocalized. They're all in the same quantum mechanical state. They're the sort of the music of the spheres as far as chemistry is concerned. And if we have a phase boundary between 2 of them, that's the most perfect 2-dimensional structure we have accessible in the laboratory. And I'm trying to think, there are not many liquids which we come across in everyday life which you can set up a phase boundary in the liquid. You can take water and you can take oil, and they will separate, but that's not a phase boundary in the single liquid. That's 2 different liquids separating. And the only one I could sort of think of is liquid crystals, which we're all used to having them in our digital displays. Liquid crystals are great long molecules in a liquid, and there are various ways of doing this, but normally they're sort of randomly orientated, and so light doesn't get through. And if we put an electric field on them, they all line up, and light does get through. So we can switch our digits on and off by just putting a little electric field on. So if we have this bit in an electric field and this bit not, we have a phase boundary between 2 liquids, so that it's the same liquid. So that's the best I could do as an analogy. And finally, we don't know how many dimensions the universe has. And in one scenario, the brain world scenario, one possibility is that we're living in a 3-dimensional surface or membrane embedded in a 4-dimensional matrix, right? Now we only understand the 3-dimensional bit, we don't understand the 4-dimensional bit. But that may possibly explain why gravity is funny. If all the normal forces are limited to our 3 dimensions, but gravity can leak out into the 4th dimension, gravity will be weak because it's lost part of its flux in the... So here's a sort of little picture. There's a force. We're doing it in 2 dimensions and 3 dimensions. So here's a 2-dimensional surface in a 3-dimensional world. If the force only sits in the 2 dimensions, it's quite strong, and if it leaks out, it's quite weak. But there are various other weird reasons why we should do this. But in the early universe, it's thought that these brains could exist. They're mobile. And if they annihilate, if we have a brain and an anti-brain kill each other, this may trigger or terminate epochs of inflation. These are periods when the universe expanded a zillion times faster than the velocity of light over a short period of time for various specious and non-specious regions. Okay, so we're nearly there. Hold on to your seat. So what we were trying to do was to make a field profile which would give a bubble of B phase, which likes to be in low magnetic field, surrounded by the A phase, which likes to be in high magnetic field. So we were trying to do a pattern like this. So this would be low magnetic field, this would be low magnetic field, and this blue would be in the high magnetic field. Okay? And we can do that by putting a coil around here in which the magnetic field goes that way, a coil around here where the magnetic field goes that way. Up here the field's low, so that's low field phase. Here the field is high, but right in the middle, these two fields are opposing each other, so that's another zero. I can make an isolated zero in a magnetic field, but I can't make an isolated maximum. I can only make a minimum. What we were trying to do is to make this model where B phase was the preferred phase with all A phase there and see how long it take the B phase to nucleate. And the theory suggests it should take a zillion times the age of the universe. I mean, this is why we were trying to do this. But as we put the field in, see, this is not very much stuff in the magnets, but then we put more and more in, so the blue high field region gets bigger. But you notice just before the field disappears altogether, there's that little point there where we just have a little tiny sliver of A phase, which is blue with B phase on each side. So that's two of these phase boundaries. So this is a brane and an anti-brane, and if we just take the field a little bit lower, they will collide. So that's a brane annihilation. Okay, that's just what I said. So that's our brane annihilation analog. And we're interested in whether such a process generates topological defects or mess in the matrix after we've had this catastrophic annihilation. And we need to look at the structure of our superfluid to see if there are any defects created. And the superfluid has a sort of texture, it has a directionality to it because there are little diners spinning around and they can point in various directions. So there's a, there's a sort of grain to the superfluid. So here's our simple experiment. It's just a tube, the slab of A phase in the middle. You don't need to know about it. All we do is we waggle some wires at the bottom which break some of these pairs apart. That makes some excitations which run up the top, and at the top we can find out how many excitations there were, so we can measure the flux running up the tube, and that will tell us how tough a time they have getting through, roughly speaking. So if there are a lot of defects, they have a job getting through, and if there aren't any, they will get through easily. So, okay, we can forget that bit. So we put the field just below the value needed to create this little layer, and then we measure this impedance. And these are the numbers we're getting, they're around 2. And note the temperatures, these are real temperatures. This is 150 millionths of a degree above absolute zero. Then we put the field in and create the A phase. So now the impedance is much bigger because it's got to go through two phase boundaries, so they're having trouble. And then we annihilate them, and the big question is, does it go back to what it did before, if nothing happened, or does it go back to something a bit higher, which would mean there's some extra mass in there which wasn't there before? And in fact, it goes back to that. So yippee, we do see these defects. So I need to put it there. Here's our scenario, right? This is the starting point, put the field up, just about to get this layer just forming. There it is. Da, da, da. And then we thin it down, and then we kill it. Bam. And there's our defects, right? Usually I get a cheer, but no. Okay, so we certainly see defects in our metric, and well, you could argue that, of course, these two aren't quite flat, so something funny is going to happen, because when they meet, they're going to meet at one point, right? And, of course, there's a big surface tension at this phase boundary, so we get the surface tension rip this thing apart. Now, that's even more violent than what we've been doing, so you could say this is unreasonable, but, of course, in real brains, here's if you put a pin in a balloon, the balloon is carefully balanced, surface tensions all over the place until you put a pin in. That kind of means that this bit isn't balanced by that bit where the pinhole is, and the whole balloon expands in a rather interesting way. But there's no reason why these cosmological branes should be geometrically perfect, and this is what the cosmologists hadn't really thought about. You know, this thing is so abstruse, and you don't have any intuition in everyday life, so this is quite good to make them think about reality. So you see something right, then this will rip apart. So, you know, our analogy is as good as their analogy. Okay, so this experiment is there to provide intuition for cosmologists, but it's an interesting comment on the unity of physics, that we're talking about cosmological processes at the beginning of the universe at enormous energies. You know, our little tiny cells, you know, at microkelvin temperatures in superfluid helium-3, and luckily we didn't trigger any inflation, otherwise, well, we won't talk about that. Okay, that's a sort of quick whiz through trying to squeeze, you know, 50 years of Lancaster low temperature physics in a few minutes. And I've been talking about the what and the why, but the main thing you've left out is the how. And these things are all going on around 100 millionths of a degree above absolute zero. So there's an enormous amount of sort of high-level cryogenic technology baggage which we haven't talked about. But that's just to give you, if you go on a tour now, just give you an idea. Here's a typical cryostat. It's in a shielded room, which means it's in a metal box, so radio waves can't get in. And it's on a 50-ton concrete block, which is lifted off the floor. See, we're 100 meters from the motorway, so I mean, every time any Stobart goes through, the lab goes, so that's vibrationally isolated. Here's the guts of it, which you'll see, that's a dilution refrigerator in a nuclear cooling stage, so that goes all the way down to 100 microkelvin. Here's some nuclear spin accession in the superfluid, and if you get the guys to talk about, this is the world's coldest video camera. This is looking at vortices with a video camera that's running at 100 microdegrees above absolute zero. And you can laugh, it's only 5 by 5 pixels, and one of the rows isn't working like in all proper digital systems. But the first, you know, the first digital camera chip, I think, had 16 pixels in a straight line. Well, we've got 25 in a square, so keep your heart out, idea.
Say thank you to David and to George for what was a great double act, and I think they reinforced each other. There are tours, as George said, and also some nibbles and drinks outside, but I think before we go, we should give our speakers another round of applause for that. So nibbles outside and tours if you want to go as well. Of course.